All right, we all ready? Yay! Okay, so reminders, we have mastering tonight and Thursday night. And don't forget, you get 3 extensions, no questions asked throughout the semester. So if it turns out you just don't have time to do homework one night, totally fine. Just email me and I'll extend it. No big deal. I understand, life happens. You may need some extra time to do the homework. Totally fine with that. Seminar opportunities, there are 2 this week. There is the biology one immediately after this class at 11 a.m. talking about blight on the American chestnut tree. Then there is the one Thursday, which is a former Berry student who is currently an analytical chemist for P&G working in quality control. And so talking about what does it mean to be a chemist in an industry. So that's pretty neat. And then if it turns out neither one of those work for you, don't forget you can also email me and I will send you a video to watch and you can summarize it on your own time. Because I understand the 11 o'clock hour is kind of tricky for some people. They work and have other clubs and things. So no big deal. Just email me and I'll send you some other options. So, all right, let's finish off the very last, like we had like 1 slide left in chapter, whatever, 7. And then we're going to move on to chapter 8. So the last thing I want to kind of do in chapter 7 is just kind of put together some practice terms, whatnot. So I guess I'm going to set it up like this. Let's say I have all right, so here are my 3 options at n. I could have multiple options at n. We're going to do just 3. We're going to do n equals 1, 2, and 3. Remember that n is called the principal level and tells us about energy, the energy of that level. All right, so let's say if I have, let's see if I can get this all onto one slide. It's real close. Well, that's not bad. All right, so if I have n equals 1, what values of L could I possibly have? 0. Anything else? No, because L is up to n minus 1. So L only has values up to n minus 1. L is also termed the sub-level. And its job is to tell us the shape of that orbital. So if I have n equals 1, my only option is L equals 0. These aren't lining up very nice, sorry. Kind of in that direction. All right, if I had n equals 2, what are my options for L to equal then? Okay. Okay, well if I had n equals 3, what are my options? Mm-hmm. Okay. So what's the next quantum number after L? NL, M sub L. And M sub L tells us, yep, orientation. And it's often referred to as the orbital. So it tells us orientation, we call it the orbital, because it kind of puts together all the other information. All right, so if I have n equals 1, L equals 0, what is the rule about what M sub L could equal? So M sub L equals minus L up to plus L. So anywhere in there. All right, so if I have n equals 1, n equals 0, what are my options of M sub L? Just 0, right? So how many shapes and orientations do I have for this combination? Right, just one, and it's just going to be a sphere. So all this together, the 1, 0, 0, that's our sphere. All right, what if I have n equals 2, L equals 0? What is my option for this combination? 2, 0. Okay. What about if I have 2, 1? How many different shapes do I have then? I have 2 shapes, possibly, and 3 different orientations, which is what we saw back there, right? It was the double dumbbell. It has 2 orbs. 1, 2, 3. Okay. That's not just that. And this way. All right, those are the 3 different shapes you can see. Not pretty. All right, so we've already done, so now I'm in n equals 3, L equals 0. This one we already know, and this one we already know. So what if I had 3 and 2? Where are my options of M sub L? Yep. So how many of all these, how many unique M sub L's are there? Right, there's 5 different ways we can rotate it around. All right, so that's when I give you all this information going this way, you can pick out the L's and the M sub L's. What if I have you guys do the other direction? And let's talk about how many 2p orbitals are there in an atom. So when I say orbitals, which letter am I talking about? The N, the L, or the M sub L?
The M sub L.
Right, so we're looking at, I want to know how many M sub L's options there are if I know 2p. All right, so the big number 2, not really big, the number 2, what letter does that tell you? N, L, or M sub L? All right, that tells me N. Okay, so P must tell me L. What number does P go with? 1, goes with 1. I'll remind you guys over here. Equals. We'll do 0, 1, 2, 3. All right, so if I have 2p, that tells me the N and the L. If I know L is 1, how many M sub L options do I have? 3. So how many M sub L's are there in this given example? 3. Okay, let's do the other practice problem. And then we'll take all this knowledge and apply it. It does have an application. It's not just because it's fun. Because it is, it's kind of fun. All right, how many electrons can I place in the 3 D sublevel. So they want to know how many different electrons can fit in a 3D combination, right? All right, so if it's 3D, what is the N value? Okay. Okay, if it's 3D, then what is the L value? Okay. What are all, like, how many different M sub L's then would there be? 5, right? Minus 2, minus 1, 0, 1, 2.
Okay, so if it was 3, it would be 7.
Yes. Yep. All right, so I have 5 different combinations of shapes. How many electrons fit into each one of these shapes? 2, right? So for each one of these, I could have a plus 1/2 and a minus 1/2. I could have plus and minus, plus and minus, plus and minus, plus and minus. So how many total electrons can fit in these 5 different shapes? 10. So if I have 5 different shapes, each can hold 2 electrons, which means altogether I can have 10 electrons sitting in all those shapes. And each electron has a unique number. So, right, all 10 electrons, I could have 3, 2, minus 2, plus 1/2. 3, 2, minus 2, minus 1/2. 3, 2, minus 1, plus 1/2. 3, 2, minus 1, minus 1/2. So each electron has its own seating. It has a unique set of 4 numbers that tells us a good place to put it, where to look for it. Yeah.
On the mastering wheel,
Mhm.
you had to figure out like whether it was plus or minus 1/2. How do you know that again?
I guess I have to look at the problem. They'd have to give you some sort of hint as to which one it was. Yeah. I know in some of the problems they were trying to do a combination of saying if you have an N, L, M sub L, M sub S combination, what's a good combination, what's a bad combination? The M sub S won't tell you much of anything. Like the only 2 options are plus and minus. Say anything other than that, it's a bad combination. But then the rest of them have to depend on these N, L, M sub L combinations. Yeah. All right, so now we have all this knowledge about electrons and how they get numbered. We are going to apply that to something you're very familiar with and figure out why does the periodic table behave the way it does. I'm sure you guys have thought about this a lot. Like, why are those elements in that order? Maybe someone's thought about that. Why are the elements in the order that they are on the periodic table? So this is officially Chapter 8. Chapter 8. It's all about periodic table and trends. All right, so the modern periodic table, which is what we use now, this version, right, that everyone's fairly familiar with. The modern periodic table is credited to Dmitry Mendeleev in the early 1900s. The current table is based on what we call the periodic law, right, which we talked about probably in like the 2nd class period, where we have the elements arranged with increasing atomic mass. And when we do that, the trends occur periodically. Periodic table is based on putting the elements in the way that they occur periodically. Okay, let's put it this way. So this is what Dimitri did. Dimitri did elements arranging with increasing atomic mass. Our current table uses increasing atomic number. It's been shown to be a little more accurate about predicting trends. So if it's really arranged using increasing atomic number, how are the atomic number for a neutral atom related to its number of electrons? If I have element carbon right here, number 6, how many protons does it have if it's number 6? How many electrons should it have? So if I know how many electrons it should have, I should be able to tell you everything about those electrons. How many there are, right? 6. What's their orientation, what shape orbitals they're in, all kinds of stuff like that if I know for sure there's 6. So because I know protons, I can find out information about electrons and figure out what their electronic configuration is for each element. So let's talk about what does it mean to have an electronic configuration. What do I mean by electronic configuration? So, all right, we've talked about the fact that quantum mechanics describes the behavior of electrons and atoms. So, an electron configuration for an atom shows which orbitals are occupied in an atom and where how many there are. So electron configuration tells us the things we want, the N, the L, and the M sub L. Tells us which orbitals there are, where the electrons found, and then how many electrons are in each orbital. So let's take a look at, we'll start off easy. We'll start off with hydrogen. All right, so here's our buddy hydrogen. If it's number 1, how many protons does it have? Okay. How many electrons should it then have? 1. All right. So we know hydrogen has 1 proton, 1 electron. Which letter N is the lowest energy? 1, 2, or 3? Okay. Okay, if I have N equal to 1, which we just says the lowest energy, what does L have to equal? Okay. If I know N and L, what do I know about M sub L? It also equals 0. How many electrons can fit into an M sub L of 0? 2. But I only have 1 so far, right? I have 1 electron. So it has an electron configuration of 1, right, from N equals 1, S from L equals 0, and the superscript 1 tells me how many electrons I have to put in that S. So I have 1s, 1 electron.
Did you say what the superscript was?
Number of electrons.
Okay.
Yep. This tells me that piece of information. Okay, what if we then look at helium? If I have helium, it's over here sitting at 2. So how many electrons does helium have normally? All right, 2 electrons. So it's the lowest energy. If n equals 1, Ls equals 0. And helium has 2 electrons, which I'm telling you right here, 2 electrons. So the superscript tells me how many electrons are in that s orbital. Okay. Okay. We can draw it a different way. Maybe that's not great. Maybe you prefer what we call orbital diagrams. So this, when I write it like this, right here, this is the electron configuration. What I'm about to draw right here is going to be the orbital diagram. They tell you the same information. It's just 2 different ways of finding out the same information. So if I was going to do a diagram, it really means drawing, right? I'm going to draw something for you. I can tell you the same piece of information 2 different ways. This tells me, right, n equals 1, L equals 0, 1 electron. I could also draw it as a little platform that we can imagine electrons live on. And I'm going to call the platform 1s, which tells me energy and tells me L. And if I have 1 arrow, it's telling me 1 electron. 1 arrow, 1 electron.
So that's an arrow, not a 1?
It's an arrow.
Okay.
Yeah, you'll see in a second why I do it kind of crazy like that. Yeah,
Does the orientation of the arrow up or down indicate the spin?
it does.
So it matters, do we always go up first?
Traditionally, we always go up first. We always assume up, which tells us +1.
Okay.
So in some ways, the orbital diagram tells me more information because it tells me N and L and the number of electrons, and it also tells me the spin number. So it actually tells me all 4 pieces of information, where this doesn't tell me m sub s. So traditionally, we draw it upright first, but your choice. Do you feel like going counterculture and go down first? I mean, you're not wrong. So the direction arrow shows the electron spin, right, which is our m sub s. And m sub s has 2 options. We can either do +1/2 or -1/2. And traditionally we showed these arrows to be, they're considered to be half arrows. Because if I put them together, they cancel each other out. But if you imagine this half arrow with that half arrow, the little halves cancel out and that's just a line. I don't know who came up with that method, but that's what they like. All right, so let's say now I have, how many electrons did we say helium had? 2, and it has the same platform, still 1s. So I draw 1 arrow up, and then I draw 1 arrow down to indicate 2 electrons with opposite spins.
Would you just continue, like if you had many electrons, would you just continue the platform up?
We're going to find out in just a second. Very exciting.
That seems like it would take forever.
Well, that's why we don't do orbital diagrams very often. It's a little more labor intensive. But some people think better in pictures, so I like to show both options. All right, so our use of an orbital diagram leads us to the Pauli exclusion principle, which we've already talked about, we just haven't officially named it. The Pauli exclusion principle says that no two electrons can have same four quantum numbers. Because as you're drawing it, you can't have two up arrows, right? You have to have a plus 1/2 and a minus 1/2. And so doing it in a picture form, you can see, oh, I definitely have this guy is n equals 1, L equals 0, m sub L equals 0, m sub S equals plus 1/2, and then all the same for minus 1/2. Yeah.
So it's in the S because there's like 2 electrons and there's only 2 spaces, so if there's 3, there's 3.
Mm-hmm. Yep. Yep, each platform can only hold 2 because there's only 2 options of m sub S. So every time you draw a line, like here, only 2 electrons can live on that platform because there's only 2 options of m sub S. And so if I had more than 2 electrons, I would have to put them in a different location, which we'll do here in a second. Work our way up. All right, and so just as, all right, here's my, just a refresher, exactly what we just did. N, L, number of electrons, or you can draw it as a box. In case you forget later, those are our 2 options. So let's talk about what happens if I have trickier elements with more than 2 electrons. So if you have an atom with more than 2 electrons, right, it's going to depend both on the N, which tells you energy, then L, which tells you which shape you're in. Okay, so we already talked about the fact that energy increases with increasing value of N. All right, we had this picture on the other page. Right, increasing value of N means more energy. So 1 is the lowest energy, 3 is the highest energy. So that means the s orbital, right, if n equals 1, L equals 0, that's s orbital. That's the lowest energy orbital we could possibly have. Means P is the next highest energy. So we've just drawn ourselves the energy options. So this is the lowest energy. then this S is the next, this P is the next, then 3S, 3P, 3D. So increasing energy this way. So let's take a look at 2 or 3 examples and see how we can build up our diagram. All right, so let's take a look at lithium. Lithium's right here. If lithium has atomic number 3, how many electrons does it normally have? 3, okay. I have 3 electrons. So what is the lowest energy combination at this point? Everybody should get it, right? Lowest energy combination of N and S, or N and L. S. All right, so 1s. How many electrons can fit in the 1s? 2. Have I put electrons everywhere? No, I got 1 left over, right? So what is the next option? Right, I just put that sheet. Okay, it can't be 1p. Oh, here it is. All right. If n equals 1, there's only one option, L equals 0. So I've used up all the electron spots in this. So then I have to go to 2s. So this one, I can only put 2 in. So if I have any more than 2, I got to bump up a level and go 2s. So I have all my electrons.
And you just write that as 1, or you put like a comma? You just write it as 1.
You just write it as like one block of information, yeah. We'll come back to magnesium. I don't think we're ready for magnesium yet. Let's do, we'll go slower. Let's do carbon. Okay, if carbon has atomic number 6, how many electrons does it normally have? Okay. All right, so what is the lowest energy combination we can put together? Okay, 1s2. How many electrons did that use up? All right, I've used up 2. How many more do I need to put someplace? 4. All right, what is the next energy level combination up? Okay. If I do that, how many electrons have I used up? 4. How many more do I need to put someplace? Okay. 1s2, 2s2. What comes after 2s? 2p. And then how many do I put in there? 2. What if I wanted to draw this as an orbital diagram rather than a electron configuration? Okay, this is what I'll give you some hints. All right, so this is 1s, right? We just did this one. All right, the platform. So 1 tells me the N, the S tells me the L. Platform tells me the M sub L. All right, there's only one solar platform. 2 electrons, that tells me the M sub S. All right, so far so good. How many different ways can I configure P? If I have 2p, how many M sub L's can I have? All right, like we have over here, 2, 1. M sub L has 3 different options. So how many platforms do I need? I need 3 platforms. And that tells me visually, right, it could be in the up and down dumbbell, it could be in the across, it could be in the this way over here. All right, so then using our next fancy principle, I don't know where I put this next. It's tradition to do all the ups first and then come back and do all the downs. I'll explain why in a minute. But traditionally, that's why. That's just the order we do it. We do all the up arrows going across first, and then we do everything else. Let's see, where do I have that? It's on my next slide, so you can hang tight on the explanation. Believe me for a second, and I'll explain why. Next slide, that we're not so far out of order. All right, ready for a more challenging one? Move up to magnesium. Oh, yep, that's all I want for now. All right, so magnesium is over here with 12 electrons. All right, so magnesium, 12 electrons. All right, so what's the lowest energy combination? Very bottom, 1s. How many electrons can I put in the 1s? 2. By the end of the class, you'll be tired of me asking this, but then you'll have it. You'll have it in your head. All right, what comes after 1s? Okay, how many electrons can go in the 2s? Okay, I've used up 4. I've got 8 more to go. What? 1s2, 2s2. What comes after 2s? 2p. How many electrons total can fit in a p? 6, right? Because there's 3 platforms. Each can hold 2, so a total of 6. How many electrons have I used up when I do this? 10. I got 2 more to go. So if I do 1s, 2s, 2p, 3s. How many electrons fit in 3s? 2. Eventually, you'll rattle this off in your sleep. 1s, 2s, 2p, 3s, 3p, 4s, 3d. Good. Okay. Let's do the challenge question I have on here. There's really a two-parter. I want to know what's the electron configuration, and then for that last electron, what's its 4 quantum numbers. So let's first do the electron configuration of chlorine. All right, chlorine has 17 possible electrons. So take a minute and see what electron configuration you come up with that has 17 electrons. Okay, 17 electrons. I want to know what are, for whatever number 5, electron number 17, what are the N, L, M sub L, M sub S for that electron number 17? So based on the fact that it's in the 3p, what's its N value? Okay, 3. What does the P tell you? L equals 1. What are the options of M sub L if I know L equals 1? So then what are the 2 possible spin states for M sub S? So any combination of that would be the possible quantum number. We'd have to identify all 5 of them to be able to pick out exactly which one it is. Okay, feeling pretty good? Feeling not awful? Okay. Let's see. Lost my stupid. Oh, here we go. All right. This should be your next slide. Don't worry, we're going to do lots and lots and lots more practice today. Lots and lots. All right, so we know that the energy of the orbitals, which quantum number tells me energy of the orbital? N, L, M sub L, M sub S. Which one tells me energies on my little letter? N, right? So energy of orbitals, that tells me N. So we can build what we consider the ground state configuration, which is lowest energy for just about any element you can imagine. So we'll do some more practice. We'll say, oh, first let me, before I forget. So the filling of the electrons from lowest energy to highest energy, n equals 1 to 2 to 3. It's called the Aufbau principle. I don't speak German, so I have no idea what that means. But I'm assuming it means fill energy lowest to highest. Probably doesn't, I'm sure it needs something else, but one of those things I always mean to go look up and figure out what it means, and I forget until it comes up again. I'm like, oh yeah, I meant to look that up. Anyway, so the Aufbau principle states go from n equal 1 to n equal 2 to n equal 3. Then the other thing is the Hund's rule. So Hund's rule is our rule that says do spin up first. And degenerate in chemistry means orbitals with equal energy. So for example, when we had the P option, right, we had 2p. Oh, here we have 2p. I have 3 platforms, all of equal energy. They're all exactly the same. It just depends. Like this one may be going along the x-axis, this one's the y-axis, this is the z-axis. Those are considered degenerate. They're all identical except in which direction they're facing. So we just fill them up first. Apparently Hund decided that was the way to do it. Someday I'll get a law named after me, and I'll be like, everyone has to do it this way, because I made a rule. That's what it says. It's a career goal for me to have something named after me. Like a constant or a rule. Law would be amazing. I don't think I can quite get a law, but I'd be happy with a constant. I could just like make up a set of numbers, call it the Sarovic constant. Everyone has to use it. I don't know in what context that would be, but. All right, so let's do some more practice. Looking at some, like, let's do, what is a good element? We'll do oxygen. All right, oxygen has 8 electrons. So what is the first platform I need to draw? Everyone's screaming. I actually can't hear the answer over all the... yeah, 1s. 1s. All right, so how many electrons live in the 1s platform? 2, right? We do 1 up, 1 down. All right, what comes after 1s? 2s. How many electrons in my 2s? 2, okay. So I've used up 4 of my 8. What happens after 2s? 2p. How many platforms in 2p? 3. Okay. So here's where we're going to use our Hund's rule. And we're going to fill up across first and then backfill. Right? So here's, I'll see if I can make it obvious. So I've used up 4. I have 4 more to go, and there's 6 spots to put them. So I'm going to do 1, 2, 3, 4. I don't know why you need a rule to say that, but we do. We have a rule. You don't like this rule? All right. Fair enough. If you didn't use it, I mean, unless I specifically asked you to do Hund's rule, I mean, there's nothing that says it's wrong to do it the other ways.
How about the spins are supposed to like cancel each other out? Or...
They do, but electrons, right, they're all negatively charged. And by preference, they'd rather have a space to themselves than share it with another negatively charged thing. You can imagine them like little magnets. And if I have 3 zones the magnets could be in, they would prefer to be in their own zone rather than sharing it with another magnet of the exact same charge. They push each other apart and run into each other all the time. So that's the concept behind it. That we would like to imagine they like their space, their elbow room. We have no idea. Electrons actually don't have personalities and can't tell us anything. So this is how we imagine if we were an electron, what we would like. So, all right, this snazzy diagram is in your textbook, in case you forget which one Hund's rule is. We fill up all the 1s's and the 2s's, and then the p's fill up 1, 1, 2, 1, 2, 3, then just like we did oxygen, fluorine, neon. So, you may be thinking at this point, besides the fact this is fascinating, you may be thinking, how the heck does this apply to periodic table? Well, I would love to tell you about that. We can apply all this to the periodic table, and it'll make figuring out everything around the periodic table so much easier. All right, I'm going to say, if you have the PowerPoint, you can look at that figure. I'm going to save it. It's going to be my exciting conclusion to this. So we can now look at the periodic table and our knowledge of electron configurations and make predictions about periodic properties. So, first thing, the highest principal number increases by 1 going down a row. And as you move across the row, the number of electrons increase by 1, right? Because the protons are increasing by 1, so the electrons increase by 1. So let's take a look at what we've already decided we know about our periodic table. Right, we said that hydrogen was 1s1. We said that helium was 1s2. Well, what happens after 1s2 if I have a third electron? 2p6. Or 2ps, sorry, 2ps1, 2ps2. How many electrons are in the 2p platforms? 1, 2, 3, 4, 5, 6. Huh, look at that. What happens after 2p6? 3s. How many can live in 3s? 1, 2. What happens after 3s? 3p. 1, 2, 3, 4, 5, 6. Look at that. It gets a little funky down here, but I can explain it. So if I was just working through it, you can have 3D, right? You can have 3s, 3p, 3d. Gets a little weird in the energy. It turns out 4s is slightly less energy than 3d. And so this is still 4s. Then we do 3d, which can have 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Then we get back to 4p. 1, 2, 3, 4, 5, 6. So by knowing where you are on the periodic table, you can know exactly the orbitals, or vice versa. If I tell you the orbital, you can exactly tell me which element it is. So it looks like gibberish. Like when you look at it, you're like, why are these two guys like towers unto themselves, and then why does it kind of make this shape? It's from the electron configuration. So And here's my, you can't really see that after all that excitement. Nope, can't read it all. Anyway, it just pretty much lays out the fact that hydrogen is 1s, 1s2, lithium is 1s2, 2s1, 1s2, 2s2. And because of that, we know where it is on the periodic table. All right, so now I know where they are on the periodic table. I would like to know how knowing that will help me figure out what kind of chemistry they can do. So, the outermost electron or electrons, depending on what we're talking about, is going to be these over here, whatever electron or electrons you name in the last orbital. So in this case, I have one outside electron. Over here, I have two outside electrons. If I did boron, it would be these three. It's whatever electrons are in the n orbital at the end. Those are the outermost.
Why would it not just be 2p1? Yeah.
Because they have the same energy. So it's different shapes, but n equals 2, n equals 2. So they have the same energy. So the outermost electrons, I'll even put up here. Which ones have the same n, same outer energy level. So if I was going to draw a little orbital diagram, I would actually put the, let's say I do boron, I would do 1s, 2s, 2p. Because that tells me how much energy they have. Okay, so those outermost electrons are called the valence electrons. And those are the electrons that can do chemistry. I wrote too big. I'm going to make myself some space over here to write some other fun facts. Let's see. All right, so those are the electrons available to chemistry. So the chemical properties of an element depend on, obviously, the protons and the neutrons, right? Because we already talked about isotopes, and we talked about protons are the ones that make the element. But we're talking about chemical properties like bonding and becoming an ion. That's going to depend on the valence electrons. Turns out the elements in the same column have same number of valence electrons. And we already know that everything who's in a column all have similar properties. So similar properties come from the same number of valence electrons. So if I was looking at my periodic table again, because who doesn't like looking at the periodic table? I have periodic tables all over my office here. I come by, I got my periodic blanket on, I got my periodic chart over here on the wall. Usually have one open on my desk. All right, so if I'm looking at my first column over here, right, this is 1s1, this was 2s1, This is 3s1, 4s1, 5s1, 6s1, 7s1. How do I know that without even really thinking about it? Well, I'm in across 1, which tells me the n, and I'm in down 1, which tells me the number of electrons. So it's kind of like a chart, like a map that tells you, well, if I'm here, potassium, I know it has 19 electrons, but it'll take me a long time to count them out. I know I'm in row 4, column 1, so it has only 1 electron. Well, it only has 1, that's 4s1. Done. Okay. And all of these have only 1 electron. Guys all have 2 electrons. So for example, let's look at 9 and 5. 7, 50 electron. So the electron configuration for both of Stu? Look at, right, 1, 3 electrons are in energy. Valence electrons. The electron also same. There's a core. Core are used, but they chemistry. They're the ones that everybody available to do. At phos, are in the same. Expecting the same number of electrons as phos have. 5. I make 10. And that's really my valence. If I'm in the sound column of available to do chemistry. How? Oh, wait. Here we go. Ion. I are over on the other one. I would love one row. Here. Please don't. All right, so electron. All right. So either electron is the stable. Take a look. Have electrons right at the one is to piece count electron key or but one I have to do right to 3 1. Let's take a look on which has 18. It's electron. I have what I would have to are these before they're set. Add any more shift to go up in energy. Your are stable electrons. They don't want their that they're away. Play card is the main there in your head. Affects ion. So let's so the do they want or right? What charge sodium typically +1 +1 is log electron. Why that is 11 electrons. 2, 2, 2, 6. That's 1 with it 1 plus. It's not be 8 electrons plus 1. What on table? I was sodium, lost an electron, and I became look at what no they're going to lose electrons to get like a nose. So what had fluorine, which had 9 normal. Just or minus. Let's take a look. That's why I like yeah. So rules. Hopefully, everybody over here get the full complement. Over here, full complement. So over here, typically 1. Here, typically minus. Let's see. Some more here in a minute. All right. What does that appear in the fact that we charge? We other types of properly function, thereby number of electrons. So that these
Or
properly talk about
just
configure cause
these
adequately. Yes, a particular charge is an electron. For all of them, do at least the. All right, atomic rate is so on a scale which halfway, like the middle to the atom,
not
and diameter across. When we
have them
we pretend
in our head,
that's big,
but we know
probably true here. The atomic radius
for the
average bond between two atoms.
Two.
Bonding. Right, so we're going to walk. Yes.
so
Let's, for
for
example, at
what two
not done. Do you just we'll do
which is
20.
go ahead and take
Electron configuration 12.
20.
Take a to work. I know question balance electrons is balance electron calcium hand. Well, about what run column column. So
For second
that's would they
half
lose some
drawn.
plus two
That way they
these two electrons and become
just yeah.
it has 20 electrons.
Health
Figure excellent.
next question
That's correct.
forward. Did you say
Calcium
calcium
radius. Yes, I do expect X.
is good?
Sorry, no. Buttons. Take a look. Will
Do
Argon, which team?
argon, it has
Full set electron. Right.
the one level. Have
And
the capability
right. Abilities.
to if
3 is energy. 3 in theory.
put more
Electrons.
so
Argon
the
one gave electrons
it's
ahead.
so
Back
to
to
all your for
what? How likely
to
share
favorite. So most
don't want to
all
look in the
so
and pull
PS
small. The R is think about
shares
into
itself
right. Because the nuclear is happy with that number
so
there.
your text
Being textbook
it's
much easier to see at rate
equal
right. Go
Going-
makes sense. You need more with them.
as
We get
big
some no
still
here.
electric can't
CM has 100 strum. Argon smaller.
all right for
You guys quiz today. Rubber.
for
Or what we
say
and what today. Chapter
say
9